We can see the allotropic nature of iron and the cobalt. Okay, these two are the having the allotropic nature. What do you mean by allotropy? Okay, change in the crystal structure. Change in the crystal structure with changing the temperature is known as allotropy in the nature. So BCC changes to FCC and FCC changes to BCC again at 1400. This change in temperature with the change in structure is known as allotropic nature of iron. So iron is having this particular nature and this is shown in iron, and because of this we can see that iron, all the points what we get in the allotropy, they can be seen on the x and y axis. So y axis will tell you all the temperature from 0 or room temperature to melting of the iron. Okay, so we can plot all the allotropic point, that is at 727, second point at 910, third at 1400, and fourth at 1539 degrees centigrade. Okay, then on the y-axis, the axis denotes temperature in degrees centigrade, and the x-axis denotes the carbon percentage in the metal. When we can talk about the alloy of iron with the carbon, we can talk about iron-carbon diagram or the phase diagram, which is known as iron-carbon equilibrium diagram. Okay, what do you mean by equilibrium? Equilibrium means at any given point, the two phases, they are in equilibrium with each other, means they are not having the change in temperature. So what we are going to see at that temperature. Okay, we are going to plot on the x-axis, the maximum one is 6.67. The reason is 6.67 carbon, maximum carbon in cementite will alloy with the iron. Okay, so maximum is 6.67. On the x and y axis, we can plot different points with the change in carbon. Carbon is having all the metal, or in iron, all the carbon is going in the interstitial form. Interstitial means the remaining atoms which are nearby, they are experiencing the compressive stress. Due to the compressive stresses, the strength of material, or the stress, you can say, the stress is increasing, the strength of material is increasing. That is the reason why the low carbon steel are having more hardness or more strength. Is it right? No. Low carbon steels are having lower strength and lower hardness, and high carbon steels are having higher hardness and higher strength. This is due to the percentage of carbon, right? More is the carbon, more is the hardness, lesser is the carbon, lesser is the hardness. Now you can determine about the phase hardness when we will discuss further. Okay, what we are going to plot? We are going to plot the carbon solution in the different phases at different points or at different temperatures, and then these points we are going to join with the smooth line, and then we are going to get a diagram which is known as iron-carbon equilibrium diagram, okay, or the phase diagram. We are going to plot first all the allotropic nature points, that is at 727, second is at 910, third is at 1400, and fourth is at 1539. Then we are going to plot the carbon percentage. Maximum carbon which dissolves in delta is at 1492 degrees centigrade, that is 0.18. We are going to plot at the same temperature the second point, that is 0.18, and we are going to plot the third point, that is 0.55, that is the solubility of carbon in liquid state. We are going to join these 3 points together by the smooth straight line, right? Now we are going to join these 2 points. Now at 1147, at 1147, the solubility of carbon in the gamma is 2%, solubility in the cementite is 6.67, and we can have the third point, that is the eutectic point, at 4.3% of carbon at 1147. So we are getting the 3 points, 2%, 4.3% and 6.67%. Right? Now this solubility of austenite, which changes from 0.18 to 2%, will decrease again from 2% to 0.8%, that is a eutectoid one, and it again changes to 0%. Okay, so we are going to get this loop. This loop is known as austenite loop. Okay, now this loop from the room temperature till 910, you are not getting the change in the structure, so alpha is there. So what is the maximum percentage of carbon in alpha at 910? It is 0. At 727, this is 0.025, and at room temperature or 0 degrees, this is 0.008. We are going to join these 3 points together, okay, and we are going to get this line. Now we are going to get 3 points, 0.025, 0.8, and third point is at 6.67. We are going to draw the straight line. Then we are going to join these points with the point 1 with the 1400, again 1400 to 0.18, okay, 0.18 to 2 decreases to 0.8, 0.8 to 910, that is 0. Okay, then from this 910, we have already found this loop, that is 910 to 0.025 and 0.025 to 0.008. So this loop is done. Okay, now this loop, we are going to join the 1539 to this point, that is 0.55, 0.55 we are going to join with the 4.3, and then we are going to draw the straight line till 5, and then we are going to draw the dotted line. This is because of the sublimation of carbon. Sublimation means carbon, when you are giving the heat, rather than going from solid to liquid, directly it goes to solid to gaseous state. That's the reason we are not having the final melting point. One thing. Second is, carbon is the element which makes the material more brittle in nature. Okay, because more is the carbon, more is the stress, more is the strength, and more is the cement type, that is a phase which is hard, more is the hardness. So in more than 5% of carbon cast iron, the hardness is very high. So high hardness will give you brittleness, and this is not used in practical application. So nowhere the cast iron is used as a hypereutectic or more than 5% cast iron. So we are restricting till 500, and this line gives you when the liquid or the solid goes in liquid, which is not known to us due to the sublimation nature of the carbon. Okay, then we can plot all the points together, and the straight line, this straight line, this straight line is known as ferritic reaction. One solid will react with one liquid, will give you another solid, is known as ferritic reaction. One liquid will give you on decomposition as austenite plus cementite, and these two solids, one liquid will give you two solids, is known as eutectic reaction, and one solid on decomposition gives you two solids, that is ferrite plus cementite. They are known as eutectoid reaction. Now in the next lecture, we will see all the critical temperatures in the iron-carbon equilibrium diagram. Thank you.